How easy is it to find a new species in paleontology? Actually, very easy indeed. How easy is it to tell whether you've got a new species? Well, that's the hard part. In this video, we'll go through the process with a possible new species of crinoid found near our home in central Wales, and we'll see whether it really is or not. Hello again and welcome back. Some of what I do on this channel is about the big questions in the history of life, and that's brilliant. I really enjoy that side of it, but I also want to show you more about the sort of nuts and bolts of how paleontology works, the processes we have to go through to try to come to conclusions and so on. So this is one of those sort of subjects. I'm going to be looking at how we work out whether an interesting discovery that we make is likely to be a new species, and the level of detail that you have to go into to work that out. It might also involve some pyrotechnics. Stay tuned for that. Right, now that you've been forewarned, onto the subject. The phrase "new to science" might conjure up all sorts of dreams of fame and fortune in people who are out collecting fossils, but the reality is often a long way away from the expectation. If you happen to find certain groups, then even a small piece of something new will immediately grab headlines, media being what it is, and will be celebrated, dinosaurs, by millions of fans around the world. If, for example, you find a new fossil sponge, however, that's going to have to tell you something really exciting in order to get the headlines. I've personally found probably several hundred new species, not only sponges but also worms, some trilobites, now all of course the castle bank stuff, all these soft-bodied creatures, and some of those of course are quite spectacular, and when they're published they do actually attract attention, but a lot basically goes unnoticed, and that's how it is in paleontology. If you're collecting things which are not immediately exciting to the mainstream media, then you will not get celebrated particularly for finding something new, but you do get the satisfaction of it. First though, you have to work out whether you really do have something new. That might seem like quite a hard job, but I'm going to show you today that you can actually do it in your study, in your spare room, whatever you've got at home, because a lot of paleontology is still very much old school. Sure, we use synchrotrons and microcomputed tomography and stuff like that when we got it, but on the other hand, the process of describing and finding new species is very much about going out with a hammer and then looking carefully at things in the right way, often using fairly basic microscopes and techniques that have been around for decades, if not centuries. First, I need to introduce you to today's fossils, which are crinoids. Sea lilies is the common name, although they're nothing to do with plants whatsoever. These things, with all these massive arms coming up here, are actually close relatives of starfish. They are echinoderms, they're in the same phylum as starfish and sea urchins and sea cucumbers, and many weird extinct groups as well. The body form is a little different to a starfish in that they have a stalk. So a long, slender stalk which leads to a little cup-shaped body and then often multiply branching arms, which are usually also slightly feathery, and these are used for capturing food out of the water and then feeding it down the arms into the mouth at the top of the body. And they are attached to the seafloor or embedded in the sediment, or in some cases they actually are really quite mobile. So many of these stalks have cirri coming off them, which are little prehensile tendrils that they can use to drag themselves along with. And when you see them walking across the seafloor, it becomes quite obvious they're not plants. There are actually some free living crinoids as well, and you can find these today around even the coasts of Britain, things called feather stars, which have lost the stalks, but they still have the body and the arms which they sort of float around and sort of flap their arms to swim with. So they're rather lovely things. But usually you don't find a specimen like this, which is not quite complete because we're missing the bottom part, but is articulated. All the pieces of the skeleton are together. Because in that there are thousands of tiny little plates. And there's not much holding those plates together. So usually what happens is the things die, they wash around on the seafloor, and you end up with slabs like this instead. Lots and lots of crinoid debris. Ossicles is the term for the individual bits of the skeleton. And in order to preserve something like this one here, or many of the other ones, or like the one that we'll be seeing today, they need to be buried not quite alive necessarily, but very recently after they died. If they spend any time washing around and decaying on the seafloor, they disintegrate. Because crinoids are such lovely fossils, they tend to have been described already if they've been found, which means that it's harder to find something new unless you go looking somewhere different. And it also means that if you find something like that, then, well, people like me tend to get excited, which means you're going to have to too, I'm afraid. Sorry. So this is the fossil we're going to be working on. Really doesn't look like much at first glance. What you can see is a series of sort of brown, rubbly looking bits on the rock. And these are little holes. There's no calcite left there. The skeleton is completely dissolved. Probably actually replaced by some iron oxides as well, which is giving it the brown colour. I've already prepped these out a little bit, so there's a lot more there than you could originally see on the surface. But we'll have a look under the microscope in a second, but you can just make out these are definitely holes and they're quite small. With one of these, you can make out enough detail to be able to see that there are very recognisable bits of crinoid in here. So there's a few sort of circular polo mint-like things with a hole in the middle. There are others which are clearly brachials, parts of the arms of crinoids because they got the Pac-Man shape. And then there's this conical thing here, which is what I get really interested in. Okay, let's put it under the microscope. Alright, this is one of the little masses of little crinoid ossicles, and again you can't see much at first glance, but you can see there's a dense array of tiny little holes with quite sort of squarish shapes, and then you zoom in and you find this thing that looks like a little Pac-Man in the middle. That is a brachial, one of the arm plates of a crinoid, and the notch in it is the food groove. So it's a very, very distinctive type of plate shape that we see. And you look further around and there are more that are just about recognisable as different parts of the crinoid. So that's okay. Then you go on to the other bit, and this is much worse preservation. It's a bit scuffed as well. But there's some plates around here which are clearly polygonal. They're sort of pentagonal, or yeah, mostly pentagonal. And these are not going to be from the arms of the stalk. They've got to be from the body of a crinoid. So that might be part of the tegmen, the upper part of the body, which is not well preserved at all. But this is the bit we're really interested in. And if you zoom in here, you can see that there are little ridges. There are very clearly defined sort of plate shapes here with smooth surfaces, ridges down the centre. It's very difficult to see because you're looking into a hollow, but there is definitely some structure there. It's also got this rubbly stuff in the upper part, which has got some impressions of plates in it, but that's a lot harder to do anything with. But the lower part, potentially there's some detail there. And it's that detail in the calyx that you really need in order to identify crinoids and interpret them. Okay, to turn a specimen like this, which is just an external mould that you can barely see the details on, into something that we can really work with, we need to make a cast. But that cast has got to be really delicate, because this is quite soft rock, and the structures that we're looking at are tiny. So we don't use plaster, that would be silly. What we use is latex. This is masking fluid that you can get from artist suppliers, and Indian ink, or some sort of archival level ink, which then you can mix them together. So just pour a bit into a plastic tub that you can put a lid on, and a few drops of the ink, and just keep stirring it round avoiding lots of bubbles getting in there, and you end up with this sort of grey gloop, which we can then apply to our fossils very carefully. Because to get a decent level of surface detail of this, you need to avoid bubbles and make sure that the latex actually reaches into all the corners and moulds the surface as precisely as you possibly can. Ideally, you really want to do this under the microscope so that you can make sure there aren't any air bubbles forming, because air bubbles are the absolute scourge of a latex cast. They will ruin it, and they'll invariably be in the bit that you really want to see the detail of. So we can do this under the microscope, and I can record what I'm showing you under here. So we've got another little piece, not the same specimen, just a few ossicles, but we can show you the same process here. So this is now recording. I will put some water on around it. There we go. Just brush the water gently over the surface. I will put the polarizer in so that you can hopefully not be distracted by reflections. Are there any bubbles there? Yep, there's one or two bubbles. Okay, a little bit of tissue to dab away at it. That should remove some of the bubbles. Okay, and now I can add the latex just around the edges. There it goes. So watch what happens when you go somewhere near the edge. It fans out over the surface, and this will, as the water evaporates or gets absorbed into the surface, will pull the latex down to create an extremely thin film that moulds the surface precisely. And that's what you really want. You want the latex to actually get sucked onto the surface and then stop there. So we'll let that dry for a moment or two. And then add more bits on top. And there you go. And we want to leave that to dry for probably quite a few hours, to be honest. And then hopefully it will come back and we'll be able to peel that off after putting an extra layer on as well. And we'll get quite a nice little cast out of that. I've also got another specimen which we found a few weeks ago at a place very close by, probably about 1 kilometre away from where we were yesterday, day before. And this is another complete little crinoid crown. There's not much of a stem on it anyway, but that is a rather lovely little thing. You can see less than the size of my fingernail, but this we will also treat with the same process, and we can see how much difference it makes with that as well. Well, it's now tomorrow. Left it overnight by a radiator, and they seem to have dried fairly nicely. And so it's time for the unveiling to see how they worked. This is actually really thin, so what I would prefer to do is put another layer on and leave it another day. But just for you, I'm going to have a look at this one first. So there's a few stages in this, but the first one is just to very carefully peel this off. So you find a little tab where you can pull it from one end. Try not to stretch it too much. So this is the relatively easy specimen to cast. So this is the quite flat one. And it seems to be coming off fairly nicely. If there's any pores that it can get stuck in, this can take quite a long time to get. That's working now. To come out properly. You don't want to tear it, of course. Okay, and there we have the first one. We'll have a look at that under the microscope shortly. Right, and I'll just try to get this one off as well. I'm not totally sure that this one has properly set, but it seems to be dry enough. I think I just didn't put enough black ink in there to make the colour work properly. Okay, these are just doing the the sort of bubbly bits of skeleton at the side, so that's coming off fairly nicely. Try not to leave any bits of latex stuck in the moulds. Okay, that's those bits, so now we've got one more. This is the bit we really want, which is quite a deep hole. So I have to try to pull that out very carefully. Okay. This isn't working very well. It's too deep and too thin. But I think it's coming out. Okay. I think that's worked. Right, let's have a look with the microscope. Okay, first the really nice one. And this one has worked very well. I'm not quite sure what the white stuff is that it's picked up from the surface, but that in itself is already highlighting all these little ridges on the plates. And you go up into the arms, you've got bits of the arm quite clear there. Yeah, I think that one will work really well once we do one more thing to this. But let's have a look at the other one. Move this across. Here it is. Okay, this one doesn't have all that white deposit on it, which makes it very difficult to see much of anything. But the mould is there, the cast rather. Just move the light around a bit. It's picked up a little bit of sort of iron oxide-y, bubbly stuff as well. So yeah, I'm not quite sure how this is going to work. But there's one more thing we're going to do to improve the contrast, hopefully quite dramatically. Welcome to the laboratory. If you want to get a nice even sort of colouring on these specimens so that they photograph well, what you need is to put a sort of a thin coating of something over the surface. And if I was in a university, I'd be using a fume hood and ammonium chloride sublimate, but sadly I'm not. So this is our kitchen. And this is magnesium ribbon. You'll notice I'm wearing goggles. That'll soon become obvious why. So I have a little bit of magnesium ribbon here. And I have my specimens on a nice little bit of card. And I'm going to apply one to the other after I set fire to it. So this burns at about 1400 degrees, I think it is, Celsius. So yeah, don't try this at home, children.
Stuart, why have you got that saucepan beside the stove?
Yeah, well I don't want 1400 degree magnesium dropping onto the floor really. I'm not sure what it does for lino. Anyway, it's great fun, magnesium. So I'm keeping this well out of the way of my fingers. Just put that into the hottest part of the flame. It shouldn't take long to start an exothermic reaction. And there it goes. Okay, so now all that smoke coming off is lovely magnesium dioxide, which will hopefully not set fire to anything else and will coat the specimens in nice white powder that's about as fine as it can possibly get. Okay, done. Okay, and here it is. So this is the really nice one to start with. And you can see now we're getting a lot more detail of the exact arrangement of the plates, which are a little bit sort of crushed onto each other, they're a bit collapsed, but we can still make out the shapes of them and the arrangement. And this lovely ridgy pattern all over the surfaces. That's rather nice. Yeah, okay, we like that one. And I think we can be fairly sure what that is going to be as well. We'll come back to that in a little bit. So the other one though, this is the problem one where we weren't seeing much detail at all. Now that is a little better. It's still not a great cast. This is one where ideally you want to do it twice because it's picked up some rubble from the surface and that's stuck to it. So that's obscuring the shape of the plates. But you can see now we have this rather lovely stellate plate here with these radiating ridges from it, which is between the radial plates. This is an interradial. And at the bottom, yeah, again, that needs a better cast. So sometimes that's just the way it goes. That is, the first cast isn't quite good enough, it picks up a lot of loose material on the surface, and that helps to clean out the mould, and then hopefully the second attempt will be much, much cleaner. So I'll have to have a go at that, but I'd have to wait another day before posting it, so I might skip that bit for the purposes of this video. But you get the idea anyway. So that is a starting point. I need to get a better cast, then I need to do more whitening, and then I need to do lots of imaging under exactly the right lighting conditions to be able to pull out the features. But we've got enough now to be able to get a basic idea of at least some of the plates on the bottom of the specimen, the bottom of the calyx. So this is a comparison of the external mould and then the latex cast, which I've flipped so that it's in the same orientation, and then also a very, very basic sketch showing the basic arrangement of the plates we can see and their ornament. And it's actually quite a distinctive combination. So we have these long radial plates with a single sort of midline ridge, and then the ones in between them have this stellate structure. And then there are some basals just about visible as well below the radials, which also seem to have longitudinal ridge. And the first brachials above the radials, there's a hint of them in one or two places. Right, we are getting somewhere. This is still nowhere near enough to do a taxonomic description, but in terms of recognising a distinctive species, it might just be. So now we know the details of the plate arrangement at the base of the calyx to some extent. We can start looking for ones that we can match it up to. And for that, of course, you need literature. So the starting point is the 3 volumes of the British Silurian Crinoidia by Stephen Donovan and a few other people. But Rosie Widdowson actually did her PhD with me at Birmingham when we were both back as young students, so I knew her quite well when she was doing this project, and it's always nice to use quite a monumental bit of work like that that's based largely on her thesis. So this is the starting point, as I say. After you've found something that might be interesting, you go back to the primary literature, all the papers that you can find in libraries and so on. If you're ever wondering how on earth you get a monograph of the Paleontographical Society, well, one thing you can do, if you don't have access to a university library, is go to your local council library and ask for an interlibrary loan. And yes, they will make a very good attempt at getting it. We've actually asked them to get obscure journals from Scandinavia before now, and occasionally it's actually worked. But something like this, they would be able to find if you need to borrow a copy of a particular monograph. It's just knowing that it's out there. So this is actually quite recent and up to date. This is 2009 to 2012 it was published. And one can look through the rather magnificent plates at the end to get an understanding of the range of Silurian crinoids that are available until you find something which looks similar. And here we have something that fits the bill. So this is Periechocrinus crostatus. Photograph on the left from the monograph, and then on the right is the original drawing from 1843 as described by Austin and Austin. So here we have a arrangement of plates that looks very similar. You've got these very strong ridges down the middle of the radial plates, and you've got stellate, sort of fairly weak ridges in the interradial plates. So what we can see there, that looks like what we need. In order to check, though, you need to go to the diagnosis. So obviously looking at pictures isn't quite enough in paleontology. So if we go to the diagnosis, we can read that out and see if it matches. So what have we got? Diagnosis. A large species of Periechocrinus with a conical theca composed of high, thin plates. Large. No. But of course we have one specimen here and it might be a juvenile, so can't really go by that. Conical theca? Yep. So that's the theca is another word for the calyx, so it's conical, yep. High, thin plates, yes, they're elongated upwards. Are they thin? Can't really tell you that. But that sort of maybe fits. But then the critical part. Median ray ridges evident. And this, if you read in the remarks, is the key feature to distinguish it from other species. It's got these median ray ridges, which are basically the ridges that we were describing in these pictures. Then arms branch asymmetrically, dividing into 7 to 10 arms per ray, typically 8. Okay, for that one, we simply don't know because we don't have a good enough arm array. The other thing to bear in mind from this is that under the occurrence data, you find that this is quite common, but is known only from the Wenlock Limestone Formation of Dudley. This is obviously West Midlands. It was a shallow marine reef environment where you get many different crinoids. But here we're well out into the basin in a totally different environment with a very small crinoid. So we have a specimen which is not that great. It appears to match a known species, but that species is known only from slightly older rocks, Wenlock rather than early Ludlow, of a totally different environment about 50 miles away. Ours is also tiny, and we haven't seen any sign of this thing getting much larger in this area. There are no isolated large plates yet, but that might not mean much at all. Possibly this was encrusting onto something like a nautiloid shell, which then swam out or was washed out into the open sea, and so it's not in its natural habitat here. How do we resolve this? The usual way, we go and find more. So this is one of those situations where we may have something which is closely related to Periechocrinus costatus, but a slightly different species that happens to share the ray ridges. However, we can't show that unless we get much better preserved material which shows the arm array, ideally the columnals as well, isolated column plates which may show differences, they may not, but it's worth looking. And so what we need is to go back to this site, find more material, and hopefully be able to resolve it finally. One thing we can say though is that this other lovely specimen here is actually a different species entirely. So already we've got a diversity in this small area, and this one appears to be a thing called Chirocrinus, which is also in the monograph and is known only from the early Silurian of Scotland, which at the time was the other side of an ocean. A small ocean, admittedly, but still an ocean. That bigger difference in age and also in the location makes this actually a more likely candidate in some ways for being a distinct species, something new, because there are no Chirocrinus known from the Welsh Basin area at this time, or at any time as far as I'm aware. So yeah, this one might well be a new species, but it's going to take very careful work looking at the plate arrangement and the details to be able to be sure if it is or not, or to be able to actually give it a name. So that's interesting at least. And this is one of quite a few other crinoids we have here, and I'm now getting an itch to start putting all of our Silurian crinoids in the area into one big box and sorting them out properly, because this is clearly going to be a lot of work. As if I didn't have enough else to do. Speaking of other things to do, there's a really interesting paper just came out today which I want to tell you about. And I've also got plans for next instalment on early sponge evolution and various other things. So hopefully there'll be a few more coming in reasonably quick succession. Right, I shall leave it there for now. Thank you again for coming along and watching, and hopefully this has been an interesting insight into how things work, especially if you're sort of making your own labs at home. Anyone can do it, honest.